Lesson number 13, Daily Summary. In this lesson, we continue to look at applications of systems of linear equations. These applications involve mixtures using percentages and travel. These applications are a bit tougher than the ones we did in our last lesson. Antifreeze is a mixture of the chemical glycol and water. So the word antifreeze, you picture this bottle of stuff. That bottle contains exactly two ingredients. One of them is water, and the other one is a chemical that is called glycol. That is the only thing that is inside of antifreeze is these two components. And the only difference between one antifreeze and another is the percentage of each of these two components. So maybe you have some bottle of antifreeze which is like 10% glycol and the remaining 90% is water, but you might have another bottle of antifreeze that's 15% glycol and the other 85% is water. So we got different strengths of the glycol in the antifreeze, but really that's the only difference between the different antifreezes. An auto mechanic keeps bottles of antifreeze in two strengths. The first bottle is 20% glycol, the rest is water. And the second bottle is 35% glycol and the rest is water. Suppose the mechanic needs to create 12 quarts of antifreeze, which is 25% glycol. How much of each bottle should be in the mixture? Okay, let's give it a shot. As usual, we start by defining variables, and as usual, if you carefully read my question, you will know what the variables should represent. How much of each bottle? Great. L and H for low and high. L can be the amount of antifreeze in the 20% concentration, and H the amount of antifreeze in the 35% concentration. Notice that we have unit words here, both of these in quarts. Okay, let's start filling in. I've got a row for 20%, a row for 35%, and a row for final mixture. And then take a look at my column headings. I've got amount of antifreeze in quarts. Then I've got percent glycol. What percentage of the antifreeze is glycol? The rest is water. And then the amount of glycol is the last column, again, in quarts. So notice I've got two quarts columns here. Really important that we keep them straight. Antifreeze is the entire bottle. Again, it's composed of both glycol and water, but this column is just the glycol part of the antifreeze. It's how much of that liquid called antifreeze is actually this chemical glycol. Okay, so we start filling in. It says we've got the first bottle is a 20% strength, so I guess that goes in the percent glycol. Don't put a 20, put a 0.20. Move the decimal point 2 spots to the left from here. And the next row, the second bottle is 35% glycol, so that's 0.35. Next up, the mechanic needs to create 12 quarts of antifreeze. So that 12 quarts of antifreeze feels like a total to me, a final mixture. Does it go in the first column or the last column? Well, it's antifreeze. That's the first column. So 12 quarts total here, not how much glycol. It's not 12 quarts of glycol, it's 12 quarts of antifreeze. And we're trying to build a final mixture, which is 25% glycol. So for the first time in any of these problems that we tackled last class, we actually have something in that bottom middle space. It's been blank on every problem we did last class and also in the activities I think. Okay, so next up is to find a home for our variables. So L is the amount of antifreeze of the 20%. So the question is, does L go here or does L go here? Well, the last column is the glycol. That's not what L is. L is the amount of antifreeze. So L goes here. And then H is the amount of antifreeze in the higher percentage mixture. Okay, and let's think about that last column. We're looking for the amount of glycol. Okay, suppose that I tell you that I have a 20% glycol solution and it's like I've got 100 quarts of antifreeze. And I want to know how much glycol I actually have. Well, if 20% of the 100 quarts of antifreeze is actually glycol, then the amount of glycol is 20% of 100. So we would do 20% of 100, which would be 0.20 times 100, which in this case is just 20. So that's 20 quarts of what? 20 quarts of glycol. But the 100 is a number that I just made up, and really the number of quarts of antifreeze in the 20% mixture is called L. And so it's really 20% of L, and it's really 0.20 times L. And so that's what we put in this last column here is 0.20 L. And then in the next row, it's the 35% solution, and H is the amount of antifreeze, the total liquid. And so 35% of H is represented 0.35 H. And I will point out yet again, the product of the first two columns is the last column, which is what we've seen every time we've done one of these tables. Okay, the bottom spot. Well, we're actually going to fill it in. We need to calculate, but it's the same pattern that we established in the rest of this last column. We did 0.20 times L, we did 0.35 times H. We need to do 0.25 times 12. It's the product of the previous two columns, which for the first time are both filled in. So 25% of 12 is 3. Okay, and now we're going to write our equations, and we've got great news because this entire table is filled in. We get an equation from the first column and an equation from the last column. So the first column says L plus H equals 12. That has to do with how much antifreeze we have. L quarts of the one kind plus H quarts of the other kind, and 12 quarts of antifreeze total. The last column has to do with the amount of glycol we have. So parts of all of the antifreeze we talked about are this chemical glycol. 0.20 L is how much glycol from the first bottle, plus 0.35 H is how much glycol from the second bottle, and I need at the end of the day to have 3 quarts of glycol in the final mixture. And that's it. Those are our two equations. Again, if you don't like the decimals in the bottom equation, you could multiply both sides of that equation by 100. And I will point out here, and if you want to check your work later on, you can. I think I've got the answers. 8 quarts of the 20% stuff and 4 quarts of the 35%. So solve with either substitution or elimination. But this is in bold, so it must be important. Note the column headings for percent problems other than those involving interest. We did do interest problems last time, and they had percentages in them. But I'm talking here the ones where you have the percentage of some stuff. You've got some whole amount of stuff, an entire amount of stuff, but then some percentage is what we're focusing on because some percentage, some part of that whole stuff is important to us. So in these kinds of percentage problems, not the interest ones, but these kinds, the first column is the whole. I'll write this up above. The first column is whole. The second column is percent. And the last column is part. And it is always that way. So you're going to have some problems in unfamiliar contexts in the activity and in the homework. But if it's one of these kind of percentage problems, you should start by putting on the outside of your table. Whole goes in the first column, percent goes in the middle column, and then the part that you are focused on, the special part, goes in the last column. So in this case, the whole was called antifreeze. That was the entire liquid. And then the part of the antifreeze that we were focused on was glycol. And that's what went in the last column. Okay, so I think we're finished with this antifreeze problem. Let's take a look at number 2. Similar approach can be used for problems involving distance, rate, and time. For all such problems, we will use the formula rate times time equals distance, or R times T equals D. This is another formula that you know very well, even if you don't know it in this context. If I tell you that I drive 60 miles per hour for 2 hours, what meaningful thing can you calculate? Well, I'm hoping that you don't feel like adding these two numbers is appropriate, right? Like 62 is not relevant for my trip. But one thing you can do with these two numbers is multiply them. And if you multiply them, you get 120. 120 what? 120 miles. That is the distance that I traveled. So you can take the rate and you can multiply by the time, and you are calculating distance, which is exactly what our formula is telling us. Irma flies her plane with the wind and makes a 450-mile trip to Saratoga, New York in 3 hours. The return trip against the wind takes 5 hours. Find the speed of the wind and the speed of the plane in still air. To be clear, this is actually how plane flights often work. I don't know if you've ever flown across the country, but the trip from the East Coast to the West Coast takes, and I don't know if I'm going to get this right, I think it takes longer than the trip going from the West Coast to the East Coast. Forgive me if I have it backwards, but there are prevailing winds that go across our country, either east to west or west to east, and literally it takes like an hour and a half longer going one way than the other, even though it's exactly the same distance, because the plane is struggling against the wind in one direction and it's getting a speed boost with the wind in the other direction. So Let's see if we can solve this problem. We're going to start by defining variables. Find the speed of the wind. That's one of the variables. Find the speed of the plane in still air. That's the other variable. In this one, I'm being very explicit, telling you exactly what the two variables should be. All you need to do is tack on a unit word. So in this case, 450 miles and 3 hours, but we're after speed. So what's the appropriate unit, including miles and hours? It's miles per hour. So we'll let W equal the speed of the wind in miles per hour. And P can be the speed of the plane in still air, that's ignoring the wind, again in miles per hour. So let's make our table here. You'll notice that this table is shorter than all the other tables. There's no third row in this table for a final or a total. So we've got two rows. We've got the with the wind trip and the against the wind trip. Those are our two legs. And then look at the column headings here. We've got the rate, and we've got the time, and we've got the distance. So let's start filling in. Irma flies with the wind and makes a 450-mile trip. Let's fill in. That's with the wind, first column, first row. And 450 miles is the distance. I'm actually not going to fill that in. Let's come back to that. It says 3 hours, so there's the time, 3 hours here. And it says the return trip against the wind takes 5 hours. So we'll put the 5 right there. Okay, and now we got to get the speed of the wind and the speed of the plane in still air. So it is like our pattern so far has been to do something like this. That is not right, so don't put that. Let's just take a quick detour. I'm just going to make up some numbers. Suppose that the wind speed is 20 miles per hour. And then suppose the speed of the plane naturally is, I don't know, 180 miles per hour. Just making things up. So here's my question. How fast will the plane go if the wind is helping? So if the wind is helping, then the plane naturally goes 180 miles an hour, but it is getting a 20-mile-an-hour boost because the wind is helping the plane. And so what do we do with the 180 and the 20 to get the real speed of the plane? We add them. So 200 miles per hour would be the actual speed of the plane when the wind is helping. But when the plane is going against the wind, what do we do? Well, it would normally be 180, but it's getting hurt by 20 miles an hour. So what do I do with those two numbers? We subtract them. So the net result there for the plane would actually only be 160 miles an hour. So that's what we have to do. We got to add the P and W, and we got to subtract the P and W. So let's do that. With the wind, the plane would naturally be a P, and it is getting helped by W. P plus W, that's what we did to get the 200. Against the wind, start with the natural plane speed, subtract the speed of the wind, 180 minus 20, that's where we got the 160. Okay, so far so good. Next up, distance. Well, take a look at our brand new formula right up here. Rate times time equals distance. Take a look at the way we've set up our columns. Rate is the first column, times time equals distance. Lo and behold, the last column is again the product of the previous two columns. 3 parentheses P plus W, 5 parentheses P minus W. Okay, and now we finally get to use this 450. It's a 450-mile trip, so that means that in this thing, this last column, which was the distances, is equal to 450. When you go with the wind, you cover 450 miles. But when you return, it's the same trip, so it's the same 450 miles. So those are our two equations written right down there. No row for the total. All right, so that's it. You solve those two equations. I guess first step would be to distribute, and then you could either use substitution or elimination. So a couple of observations about this problem, this kind of traveling problem. First of all, this is the only problem where that first column isn't just the straight up variables. You don't put P in one spot and W in the other spot. With these problems, it is always P plus W and P minus W, and it's the only one where it's not just the P and the W, just the variables. Like up above, it was just the L and just the H in this column. Was that the problem above? Yeah, L and H. Okay, next observation. It is really easy to be careless and put these numbers in the wrong spots. Or maybe not those numbers, but these two things here. If you get them reversed, if you instead were to put right up here P minus W, and right down here P plus W, you are going to get the wrong answer, because then you are saying that the part where the wind is hurting the plane takes 3 hours, which is less time than the part of the trip where the wind is helping the plane. So it can't possibly be 3 hours for the P minus W. So you got to be really careful. You are putting the smaller time value, that is the quicker trip, you better put that with the wind rate of speed, which is always the plus between your two variables. And then another common mistake I see is students doing this, W plus P here and W minus P. And these students are well-intentioned and they know that when the wind is helping, you add, and when the wind is hurting, you subtract. And they have accurately captured that phenomenon. And in fact, W plus P is okay. It's exactly equal to P plus W. But W minus P is not okay. If you do W minus P with these green numbers here, what do you get? W minus P, 20 minus 180 is negative 160. Negative 160 is not the net speed of the plane. You got to do the plane's speed first. I always think of it that way. I say, okay, this is a plane we're talking about, and the plane's natural speed is P, and so P is my starting value for both rows. And then I get the wind going. I say, okay, with the wind is helping. Against the wind is hurting. But P is the thing that initiates me writing in that column. So don't put W minus P, you'll get crazy answers. Okay, as usual, you can solve later and check your answers. Turns out 120 miles an hour for the speed of the plane in still air and 30 miles an hour for the wind speed.